Welcome everyone. We're about to dive into a story that might just rewrite what you think you know about the history of computing. Because what if I told you its origins aren't in silicon, but in ancient Sanskrit? Yeah, let's get into it.
So, I want you to start with this question. Just let it sink in. We all think of code and programming as this super modern thing, right? It's what runs our phones, our cars, our whole world. But what if the core logic, the actual idea of a perfect, rule-based system, is thousands of years older than the first computer?
All right, so our journey begins about 2,500 years ago with an absolute genius, a grammarian named Pāṇini. Now, he didn't build a machine out of wood or metal. Instead, he created something way more abstract, but just as powerful, a machine for language itself. His masterpiece is this book called the Aṣṭādhyayi, which just means the 8 chapters. And look, calling this a grammar book is like calling a modern smartphone a telephone. It's technically true, but it misses the entire point. This thing is so much more.
Inside these 8 chapters, Pāṇini laid out roughly 4,000 rules, or sūtras. And these aren't just, helpful suggestions. They are incredibly tight, powerful, and almost mathematically precise rules that are designed to describe the entire structure of the Sanskrit language.
And here's where it gets really wild. The system is what we call generative. What does that mean? It means that with Pāṇini's finite set of about 4,000 rules, you can generate a potentially infinite number of perfectly correct Sanskrit words and senses. It's a finite engine that can produce infinite results.
Seriously, the system works just like a piece of software. You give it an input, say a basic root word and a suffix. Then, the machine processes it by applying Pāṇini's rules in a very specific order. And the output? A flawless, grammatically perfect word or sentence every single time. It's a linguistic algorithm.
The parallels to modern computer science are they're staggering. I mean, Pāṇini's system had concepts that are fundamental to programming today. He had meta-rules, that's rules that control other rules. He defined rule precedence, which is critical for figuring out which instruction to follow first. He even used transformations and recursion. It's all there, 2,500 years ago.
Okay, so that's Pāṇini. But the story doesn't stop there. A couple of centuries later, another brilliant scholar, Acharya Pingala, stumbled upon a different kind of code. He didn't find it in grammar, though. He found it hidden in the rhythm of poetry.
He wrote a text called the Chandaḥśāstra, which is all about poetic meters. But he wasn't just admiring the pretty verses. No, he was doing something much deeper. He was analyzing the mathematical skeleton holding the poetry together. He was looking at its underlying structure.
And what Pingala figured out was that all the complex rhythms in Sanskrit verse could be boiled down to just 2 basic units. That's it. A Laghu, which is a short syllable, and a guru, a long syllable. Every single poetic pattern was just a different combination of these 2 things. Starting to sound a little familiar? And boom, there it is. This is the big aha moment. Pingala's system of long and short syllables was, for all intents and purposes, the world's first description of a binary number system. The long syllable, guru, was basically a 0. The short syllable, Laghu, was a 1. The language of our computers was discovered first in the language of poetry. It's unbelievable.
But wait, it gets even better. Pingala didn't just notice this binary pattern and move on. No, he developed algorithms, actual, systematic procedures to work with it. He wanted to mathematically explore all the possible combinations you could make.
So his first major algorithm was called the Prostara, which means expansion. And it's a method to generate a complete list of every single possible combination of long and short syllables for a verse of any length. And he knew that for n syllables, you'd get exactly 2 to the power of n patterns.
Take a look at this example for a 3-syllable verse. The algorithm doesn't just list them randomly, it generates them in a precise logical order. Look at the binary column. GGG is 000, LLL is 111. This is literally a computational process, the exact same principle a computer uses to list all 3-bit binary numbers. It's pure math, pure computation.
And if you thought that was impressive, brace yourself for this next one. Pingala also described a mathematical structure that you probably know as Pascal's triangle. The only catch? He described it about 1,800 years before Blaise Pascal was even born.
Back then, it was called Meru Prastara, and it had a really practical purpose. It was a tool for what we now call combinatorics. A poet could use it to figure out instantly how many different rhythms were possible with a certain mix of syllables.
Like for a 6-syllable line, the triangle tells you there are exactly 15 ways to arrange 4 long and 2 short syllables. No guesswork needed.
So, let's tie this all together now. Let's draw that straight line from these ancient texts to these silicon chips in our pockets, because there's a clear and direct bridge between this ancient logic and our modern world.
I mean, just look at the timeline. The sheer gap in time is what's so incredible. A generative grammar and a fully fledged binary system, complete with algorithms, existed for nearly 2,000 years before these ideas were independently developed in the West and eventually became the foundation of everything digital.
And listen, this isn't just some quirky historical footnote. Modern experts, like the famous 20th century linguist Leonard Bloomfield, looked back at Paninis' work and just marveled at it. He called it one of the greatest monuments of the human mind. Its logical perfection is still studied and admired today.
So what are the big takeaways here? Well, first, the idea of a formal, rule-based system isn't new at all. It's ancient. Second, the binary logic that powers our entire world, it was first discovered in poetry, not in an engineering lab. And maybe most importantly, it just goes to show you that some of the most powerful ideas in human history can be found hiding in the most unexpected places.
Which really leaves us with one final, fascinating question to chew on. If the blueprints for computer science were lying there in ancient grammar and poetry all this time, what other revolutionary knowledge is still out there, hiding in plain sight in old texts and forgotten disciplines, just waiting for someone to connect the dots? Thank you for joining me on this one.